This is the 38th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. This video discusses branch instructions. When you first learned to program, you probably began by learning how to use variables and write expressions. For many of you, the next topics were selection and repetition, better known as if statements and loops. The key instruction to make both of these constructs work is the conditional branch. In general, we can use the term branch to refer to any instruction that tells the CPU to execute something other than the next instruction in memory. Jump instructions are unconditional branches. They always result in a jump to the target address. A branch is called conditional if whether the program flow changes depends on some condition. MIPS provides two conditional branch instructions: branch if equal and branch if not equal. Branch if equal looks like this. It compares two registers and branches to the target if the two registers are equal. Branch if not equal only branches if the two registers are different. And just so you're aware, the use of terms like jump and branch can differ very slightly between CPUs. In MIPS, we tend to use the term branch only for conditional branches like BEQ and BNE. However, I've seen people when talking about other CPUs occasionally use the term branch to also include unconditional branches. Fortunately, the intended meaning is usually clear from the context. So let's quickly look at some assembly code with branches in it. So just like the example with the jumps, we mostly here have instructions that initialize registers to a constant value. And then we have this branch instruction. And the idea is, if T2 and T3 contain the same value, we'll jump down to the target, we'll skip setting 4, 5, and 6 and go to 7, 8. So if we step through the code and we initialize T0, T1, T2, T3, and now we're at the branch instruction, you can see right here that T2 and T3 are both set to 2. So when I execute this branch instruction, control jumps down to the initialization of T7, which is where I put the label. If I come in here and give T3 a different value and step through the code, now T2 and T3 don't have the same value in them, so control just continues on to initialize 4, 5, and 6. In MIPS, BEQ and BNE are the only two actual hardware branch instructions. Other conditions are actually pseudo instructions. So for example, if I change this BEQ to BLT for branch if less than, and we look at the code, we can see that that BLT instruction is actually a pseudo instruction. It turns into a set less than with a branch conditioned on the result of that set less than. And that is true for other sorts of branches like branch if greater than, branch if less than or equal, and so on. So let's look at the branch if equal machine instruction. As with our sample jump, let's assume the label target refers to this address. This machine instruction requires an opcode, 2 registers, and a target address. The opcode and 2 registers take up 16 bits, leaving 16 for the target address. Notice that this is the same pattern as the add-I, and-I, or-I, and so on. Therefore, like those instructions, it's considered an I-type instruction. So how do we fit the 32-bit target address into the 16-bit space we have available for it? One idea is to try a similar approach to what we did with the jump instruction. So that would mean drop the 2 lowest bits, because they're always 0, place the next 16 bits in the machine instruction, then assume that the target address's most significant bits are identical to those in the branch instruction. This isn't a terrible idea, but it's not what MIPS does. It's possible to make it work, but there is a situation where it would get a little ugly. Let me explain. Assuming that the first 14 bits are the same for both the target address and the branch instruction itself, partitions the address space into 2 to the 14 segments containing 2 to the 18 bytes each. Since each instruction is 4 bytes, that means each segment holds 2 to the 16 instructions. If a branch and its target happen to both be in that same segment, everything works as planned. But what happens if a branch instruction happens to fall near one of these boundaries, where the branch instruction is in one segment but the target is in the next? The assembler would have to watch for this situation and write the code differently to handle it. So what would that code look like? Because it makes for a good test question, I'm not going to give the answer here. But know that it can be done. We've already seen cases where the assembler writes special code for special cases. For example, when an add i's immediate value is larger than 16 bits. So although the assembler could handle this case, it is better to avoid it if possible. One reason is that the special case would require an extra instruction. So since we're going for a good performance, how else could we encode the target address? In particular, is there a way to avoid that potential for an extra instruction? So let's take some inspiration from file systems. So here I'm in the directory for one of my own coding projects. And here we can see the full path name for this project and the contents of the project. In particular, note that there's a source directory and a lib directory. And now I'm going to change into the source directory. Notice I just had to type cd source. I didn't need to give the absolute path of that directory. I didn't have to type in /user/kermesd/document/code/dlunit/java/src. Right? I wanted to go into the src directory, so I just typed cd src. Now I want to run the Java compiler, but reference a jar file in the lib directory. So I have two choices. I could type out the absolute path name of that jar file, which is a little bit long and tedious, or instead of an absolute name, I can just use a relative path name. I can say go up a directory, go over to the lib directory, and get me jls.jar. So how can we use this concept of absolute and relative paths to find a better way of encoding the target address for branch instructions? So keep in mind that the jump instruction uses an absolute address. It puts as much of that 32-bit target address in the instruction as will fit. But what would it mean to use a relative target address instead? Well, a relative file path means you tell somebody how to get there from where you are. Like when I did ... to go up a directory, instead of starting at the root with /user/kermesd and so on. So how about if we specify the target by where it is from the current instruction? In other words, as an offset from the current instruction. If we do that, then we don't have to worry about crossing that segment boundary. We just have to make sure that the target is not too far away from the branch instruction. Which, since the branch instructions are usually used as part of loops and if statements, the target will be only as far away as the closing curly brace. With a 16-bit signed integer for that offset, we just have to make sure that our target isn't more than 32,768 instructions away, either forward or backward. And that seems pretty safe. I've never seen an if statement or loop contain thousands of lines of code. I'm sure it's been done somewhere, but that would be exceedingly rare, far rarer than a branch that happened to cross that segment boundary. So what MIPS does for branches is it sets up the machine instruction so it contains the opcode, the two registers, and the difference between the target address and the program counter divided by 4. As with jumps, we divide by 4 because all instruction addresses are multiples of 4, and there's no need to encode the last two zeros. Also, MIPS calculates the target address based on the new value of the program counter, that is PC plus 4, instead of the current value, because it simplifies the process of building a pipeline CPU later in the semester. So now that we know how the machine instruction is encoded, let's see how the CPU implements that instruction. So as with jump, the basic process is to calculate a new target address, and then place that new target address in the program counter, which causes the CPU to execute that instruction next. But this time, we should only modify the program counter if the condition is met. To calculate the target address, we take the immediate value that contains the number of instructions away the target is, add back the two zeros that we left out, and then add this offset to the updated value of the program counter. And now we pass this value through a MUX so we can control whether or not we're taking the branch. This time, however, the MUX's selector is not simply a control wire. Think about it. When should the selector wire have a 1 on it? Well, it should only have a 1 on it when both the instruction is a branch and the two source registers are equal. If either of those conditions is not met, we want to run the next instruction as normal. All right, so let's add a control wire indicating whether or not the instruction is a BEQ. Now the next question is, how can we tell if the given registers are equal? Well, we could add an is equal operation to the ALU, but it turns out we can get an answer with existing operations. So which one can you use to decide if two registers have an equal value? You just have to subtract. If the two registers are equal, their difference will be 0. Now at this point, we do need an additional output to the ALU to tell us whether its result is 0. This 0 output works for any ALU operation, not just subtraction. So now we need only add an AND gate to verify that both conditions are met, and then we can send the output of that AND gate to the MUX. Notice that if the source registers are not equal, then the 0 wire will have 0 on it, which means the AND gate will pass out a 0 output, making the MUX pass through the default value of PC plus 4, and the branch won't be taken. So that's how the branch if equal is implemented. Branch if not equal is implemented in a similar manner, and we'll leave the details for a homework or a project. So to summarize, remember there's two kinds of branches. Unconditional branches that always run the target instruction. In MIPS, this is a jump. And there's also conditional branches that only move to the target if some condition is met. In MIPS, there's only two of these conditional branches implemented directly in hardware, branch if equal and branch if not equal. All the other branch instructions are actually pseudo instructions. The MIPS branch instructions specify the target using an offset from the program counter. They tell you how many instructions away you're branching, as opposed to specifying the complete absolute target address. And to be precise, the offset is given from the address of the next instruction from the program counter plus 4. And we'll see why that is when we get to pipelining in a few weeks. Finally, remember the ALU has a 0 output that tells you whenever the ALU's output is exactly 0. And that's true regardless of the operation. This works for all operations, not just subtraction. In the next video, we'll look at some examples of assembly code using branches.